Hi, my name is Lakshya Jain, and I'm gonna start with my project discussion on uh, causal discovery through structured interventions. Um, so this was done in an environment that is a gym environment, which is an Atari game called Montezuma's Revenge. So this is my project for the course probabilistic reasoning and learning, which is the CSE 598 course, and I'm gonna start with my talk. All right. So what is causal inference? It is figuring out how one thing or event affects another event. Uh, so, for example, does smoking uh, affect lung cancer in any way, and then can changing someone's diet improve their health or not? So why should we care about these questions? This is important in real life, from helping doctors make better decisions to guiding government policies to pretty much any decision that we can make. And it helps us learn how to avoid spurious correlations. Um, on the right is an example of what generally a causal graph would look like, how uh, events like winter affect holiday season, or how it affects rainfall, and so on. Uh, so traditional models like causal Bayesian networks are usually computationally expensive for tractable inference, and they are generally intractable. But that is what I have used in my project right now, instead of going for a more tractable model, which was because the structure learning for causal Bayesian networks was a lot simpler to deal with compared to those other models. So, what is spurious correlation, and why should we care about causality? Um, well, this is a pretty funny slide. So, the I keep reusing the slide because it's very funny. The number of Will Smith movies uh, that Will Smith has appeared in, apparently it correlates directly with um, pretty much directly with the electricity generation in Kosovo. As we can see, uh, when Will Smith movies go up, electricity generation in Kosovo also goes up for some reason. Um, uh, so what I think about this is that it's a spurious correlation, that these things are generally not connected at all. uh, what we usually look for when two variables move together is either A causes B, or B causes A, or there is some unknown co-founder that causes A and B both, or we can say that A and B are completely unrelated and then they're just correlated by chance, which is what I think is the case in both of these graphs, which is pretty obvious to us. But to certain decision making systems that use correlation based uh, thinking, uh, this would make a this would still make sense to these systems which we are designing, which make decisions based on correlation. So uh, it is very important to avoid spurious correlations when we are making decisions. Now, coming on to Pearl's causal hierarchy, this was originally developed by Judea Pearl, and there's three levels of reasoning according to Pearl in the causal hierarchy. You start with associational reasoning, which is seeing and observing your environment, of how uh, variable x changes with y without doing anything. So if you just keep observing, you will eventually lead to some correlations. You will see correlations and patterns in the stuff, and then you can make inferences using that, which is what most of our machine learning algorithms and RL algorithms at this point. They operate at the associational level. So my aim is to go higher up that ladder towards interventional reasoning. Interventional reasoning is when you start doing or intervening in on certain variables and observing the effects on other variables or the same variable as well. So questions like, if I take this aspirin, will my headache be cured or not? Or what happens if we stop using cigarettes? Does the cases of uh, having lung cancer go up or down? That is something that is interventional reasoning, where you start messing with some of the variables and seeing what how it affects the other ones, or at least reasoning about it. The third is counterfactual reasoning. So that is imagining or retrospection. So you can imagine things about the future. Had, what if I do this, what, or you can imagine things about the past. What if I had not done X? What would happen to the environment if I had not done this? So questions like, what if I had not smoked in the last 2 years? How would it affect my life? So we can think about these things, uh, which gives us a lot of imagination power, which gives us uh, the power to create stories or myths, and at the same time, it gives us the power to uh, uh, make inventions and think about discoveries about how this would differ if this was not a law, and so on. So, in the information hierarchy, for associational reasoning, we can use Bayesian networks. For a higher level of reasoning, which is interventional reasoning, you need a causal Bayesian network, which is what I will be working on in this project. Uh, and for a higher level of reasoning, you need a structural causal model, which is essentially a causal model of your entire environment in that uh, causal Bayesian network, uh, which you can use to infer counterfactuals as well. So I'll lead with structural causal models and what they are. So structural causal models, they represent environments via relationships and their causal. Uh, uh, so how all of the variables in your environment are connected to each other. Once you figure that out, you have a structural causal model. So basically, a blueprint for understanding the underlying causal structure and moving beyond just observed correlations is what a structural causal model uh, represents. Yeah. So now let's talk about what an intervention is and what observation is. All right. So I'll start with this example and then move to the next, which is very similar to this one. So if you have a causal model, causal graph that's like this, age affects drug and headache, and then you now want to assess the effects of what changing the drug would do to a headache. So you just uh, change the drug from whatever value it was earlier to yes now, and then you observe what happens to headache. Now you have a mutilated causal Bayesian network, which had a link here earlier, but now it doesn't have that link because you uh, purposely changed X. So now all the links that lead to X will now be broken because you have now changed X value on your own, and then you observe what it does to headache. So that is what an intervention would mean. So how do you do causal inference and how do you learn the causal graph of whatever? So to do causal inference, you need to uh, essentially you need to intervene and look at the interventional data. So now you have observational data, which was just observing, and now you have interventional data, which happens once you deliberately intervene into a variable, knowing what you are doing to that variable. So you turn on treatment, and then this link gets cut off because now you have a mutilated causal graph, and then you just observe what the health outcome is and how it changes. Now, an interesting concept that I came across that I am working towards in this project is a causal reinforcement learning. So now, causal reinforcement learning essentially integrates causal inference with RL, and then it uses interventions to learn a causal graph of governing the environment. So the environment will have a causal graph that is structural causal model which defines all the causal connections in the environment, and then my agent is in learning a causal diagram, which is a smaller causal graph, which is usually a subset of the structural causal model. Based on the interventions that it's performing, it is updating this causal graph continuously, and with that you can do actions which are interventions on the environment, and then observe the effects, and then you can do observational interventional reasoning, and then eventually counterfactual reasoning once you have the structural causal model. And this integrated with some reward function and then feedback of the state makes it into an RL kind of a problem. All right. Um, so we discussed about what an intervention is. We discussed about what an observational distribution and interventional distribution is. So once you, so this is how you show it mathematically with a do operator. So once you do x equal to 0, and then you observe um, the average treatment effect, that becomes the interventional distribution stuff. And if you're not doing anything, it's the observational distribution. And how it differs from conditioning is just conditioning is observational, purely observational, and then intervention is actually intervening and looking at the interventional distribution after the um, intervention is done. So so there are two ways of working on stuff. You can either actively intervene in your environment and look at what happens, or you can just do calculus and uh, kind of estimate what would happen if you had done this. So that is why do calculus is important. But in my case, I'm doing active interventions in an environment because I'm working on a game environment, and it's like a benign game. It doesn't really affect anything in the world. So I will be doing active interventions and not be working with do calculus in this project. But this is how people work on things. So of policy learning, another reason I'm working with active interventions is because I am doing all the interventions and the agent is observing these interventions and uh, making a causal graph out of it. So it is still interventional data that the agent is receiving, but it's not the agent that is doing these tasks, because I would have to design a policy which is a bit of a task, extra task that I didn't want to do. So I'm doing off policy learning, that is me making me playing the game, and then the agent looking at me playing the game and making a causal graph out of it. So I collect my demonstrations of human plate trajectories, and then these serve as of policy data, either human plate trajectories or just random data would also work for this initial phase of the project, which is what I have implemented till now. And then it uses the collected demonstrations to learn about the environment structure, and then make a causal discovery graph out of it. So it analyzes the sequences of actions and observed outcomes. So it has a fully observed game, which allows it to observe all the variables that are changing and my actions. And so these kind of cause and effect patterns, whenever it identifies consistently. A pattern like when a key is acquired, the door can be unlocked. So when I have a key in my inventory and I go to the door and I use key, doors unlock. And when I don't have that key in my pocket, in my inventory, then it doesn't work. So that is how the agent identifies how to create a causal connection. And then it also identifies uh, updating those connections once it has evidence against the current belief. So, integrating these insights into a causal Bayesian network and then refining these graphs, that is, updating the graphs as new evidences are observed. That is what the agent is doing. Uh, so, it maintains an evolving internal causal graph, which is a subset of the causal structural causal model of the world, and then it keeps improving uh, the graph according to whatever it sees. So I have a symbolic grid world set up, which I'll be showing in a bit, and then I have some pre-planned interventions that are set up, which is like me demonstrating to the agent what uh, what is going on. And once the agent has learned a causal graph from this grid world, I have employed this agent to try and um, work on the gym environment from Montezuma's Revenge. So, and I've done structured learning with a PC algorithm, which tests conditional independencies to infer causal edges and then identifies which objects influence which outcomes directly. So, so I'll first show what my thing looks like. So this is the agent doing some actions in the world, and then some of these are interventions in this grid world, which I prepared for the start. So once it learns a structural causal model through this grid world, uh, or a structural causal graph through this grid world, which may or may not be the whole model, it will then move to Montezuma's Revenge environment and then try to implement whatever it has learned uh, into the game. So, this is essentially a curriculum based learning approach where I have three stages of curriculum. Yeah, so this goes on for a while. So I have uh, I'm doing a lot of steps per episode and then a lot of episodes. So a total of long uh, thing. So I will stop this and I will move ahead. So once it has correctly identified simple dependencies, that is key unlocks store, and then uh, so I start from simpler tasks, and I have three levels of curriculum, which I have in my report. Uh, then I had some inference challenges because causal Bayesian networks can become intractable in recently large state spaces. So whenever I try to do multiple rooms in an environment, it kind of doesn't infer properly, and then it gets stuck, which I will show what it looks like. This video is so at the start, this is me playing the game and demonstrating what it looks like to the agent. It uh, forms a general causal uh, graph using this. But then when I try to get the agent play this game, it gets stuck a lot in like loopy situations where it's just not doing anything. It just keeps going from one room to the other. But eventually it does avoid enemies, and it is able to do one task, that is collect the key and open the door. Alright, so that is going to be it for this presentation. In conclusion, I am able to learn a causal graph of the world, but then inference with that graph is a bit difficult. So I want to implement a more tractable model in the future and apply this in some other domain that I'm working on right now. So thank you, and I will be uploading the report as well with a lot more details.